Children, I hope you have gone through my previous video, and today we will continue further. Children, today we are going to study about isomerism in complexes. Now first let us discuss the types of isomerism. Now in coordination compounds there are two basic types of isomerism. First is structural isomerism and the second one is stereoisomerism. In structural isomerism, you have ionization isomerism, hydrate isomerism, coordination isomerism, and linkage isomerism. Whereas in stereoisomerism, you have geometrical isomerism and optical isomerism. Now let us start with structural isomerism. First is ionization isomerism. You know, structural isomerism is isomerism which arises due to difference in structures of coordination compound. Now in this, the first type is ionization isomerism. Now in ionization isomerism, the compounds which have same molecular formula but give different ions in solution are called as ionization isomers, and it is due to exchange of groups between coordination sphere and ionic sphere. Like for example, see over here, CONH3 whole 5 Br SO4 and CONH3 whole 5 SO4 Br. Now in the first case, coordination sphere contains CONH3 whole 5 Br. In the second case, coordination sphere contains CONH3 whole 5 SO4. Okay, and ionization sphere in the first case consists of SO4, whereas in the second case it consists of Br. Similarly over here, PTNH3 whole 4 Cl2 Br2. So in this, PTNH3 whole 4 Cl2 is coordination sphere, Br2 is the ionization sphere, and here PTNH3 whole 4 Br2 Cl2. So in this case, the coordination sphere is PTNH3 whole 4 Br2 and ionization sphere is Cl2. So it will ionize, the first one will ionize to give bromine ion, second one will ionize to give chloride ion. So this is the ionization isomerism. Second type of isomerism, it is called as solvate or hydrate isomerism. These are isomers of a complex which differ in the placement of water molecule in the complex. Now see over here, we've given an example, CrH2O whole 6 Cl3. Now this is violet in color, it is anhydrous. CrH2O whole 5 Cl2 dot H2O, this is light green in color, monohydrate. And CrH2O whole 4 Cl2 Cl dot 2H2O, it is dark green and dihydrate. Their properties are also different. So see, in the first case it was anhydrous because none of the water molecule was in the ionization sphere, all were in the coordination sphere. In second case, it has one ionization water molecule in the ionization sphere, and in the second and third case it has two water molecules in ionization sphere. So this type of isomerism in which water molecules position is differing, whether it is in coordination sphere or ionization sphere, this is known as solvate or hydrate isomerism. The next type of isomerism is called as coordination isomerism, when both the positive and negative ions are complex ions. An isomerism may be caused by interchange of ligands between the anion and cation. This arises if cationic and anionic metals have same coordination number and charge. For example, CONH3 whole 6 CrCN whole 6 and CrNH3 whole 6 COCN whole 6. Now in this, you see, in the first case, coordination sphere consists of CONH3 whole 6 and the second coordination sphere is CrCN whole 6. Now in this, CO and Cr are the central metals. Alright, now in the first case, the cobalt is attached to ligand NH3, but in second case CO is attached to ligand CN. Alright, similarly Cr is attached in the first to Cn, and here Cr gets attached to NH3. So there is an interchange of the ligands between two central metal atoms. Similarly here, another example, Pt NH3 whole 4 Cl2 Pt Cl4. Now in this case this becomes Pt NH3 whole 4 and this becomes Pt Cl6. So in this second case the central metal was the same in both the cases, so now there is a change in the ligands. Here only NH3 whole 4 and in this one Cl6 instead of Cl4. So these type of isomerism, that is called as coordination isomerism. The fourth type of structural isomerism is called linkage or structural salt isomerism. It is an isomerism in which ligand may attach to central metal ion of complex in different ways. Especially for this is applicable for ambident ligands. You know, ambident, which can attach through which can form a coordinate bond through two atoms. So example is CONH3 whole 5 NO2 Cl2 and CONH3 whole 5 ONO Cl2. So in the first case attachment is through nitrogen atom, in the second case attachment is through oxygen atom. Okay, so the first compound is red in color and the second one is yellow brown in color. So these are the four types of structural isomerism which can be seen in coordination complexes. Next type of isomerism is stereoisomerism. Stereoisomerism is isomerism in which different atoms or groups of atoms occupy different spatial position around the central metal atom. It is of two types. First is geometrical isomerism. This is due to the ligands occupying different positions around the central metal atom or ion. When ligands occupy adjacent positions, they are termed as cis form because they are closer to one another. And when they occupy opposite position, they are termed as trans form. So this type of isomerism is not shown by compounds having coordination number 2, 3 and 4. Alright, it is very common in square planar and octahedral coordination entities, but not very common in tetrahedral coordination entity. Okay, so in this we will first study about square planar complexes. Now square planar complexes, 1 minute, let me get to the video. This is square planar complex. Now in this square planar complex they have coordination number 4 and they are of the type MA2B2, MA2BC, MABC2 and MABCD. They can exist as geometrical isomers. Now A and B are neutral ligands whereas C and D are anionic ligands. In square planar complexes 1, 2 and 3, 4 and 1, 4 and 2, 3 are cis with respect to each other, while the position of 1, 3 and 2, 4 are trans to each other. So let us see over here. This is a central metal. It has 4 ligands, 1, 2, 3, 4. Now A, B, B, this is cis because they are closer. A is closer and B is closer. Now, but when they are, because they were placed in an adjacent manner, but when they are placed oppositely like this, then it becomes trans. When A, B, so it becomes trans. For example, see platinum and this is PY and NH3Cl. So this you will see, although these two are different, so you don't have to be concerned about this, but these are the same. So pyrimidine bases, they are adjacent and close to one another, so this is cis, and here they are opposite one another, so this becomes trans. Alright, next we come to octahedral complexes. Now in octahedral complexes, 1 minute. Octahedral complexes, see the diagram over here. For octahedral, 6 ligands are attached to the central metal atom. Okay. Now coordination number becomes 6. Geometrical isomerism is shown by the octahedral complexes of the type Ma4B2, Ma2B4 and Ma3B3. In octahedral complexes, positions 1, 6, 2, 4 and 3, 5 are trans, while others such as 1, 2, 1, 3, 2, 3, 6, 4, 4, 5 and 1, 5 are cis to each other. Alright, now some important examples of geometrical isomerism in octahedral complexes are given below. First one is Ma4B2 or Ma2B4 type, this one. Now Ma4B2 or Ma2B4 type example is CrCl2 NH3 whole 4 Cl plus ion and CO NH3 whole 4 plus ion. Now see here, first case, central metal is cobalt, 4 NH3 ligands are there, so 1, 2, 3, 4. Alright, and Cl2 are there, so Cl and Cl. Now this Cl, they are close to one another, so this form will be cis form. But in this case, you see, Cl is placed opposite to one another. See, one is here and the other one is here. So this form becomes trans form. Alright, here also, in this case also you see, Cl is close to one another, 1 and 2. So this form is called as cis form. But in this case, they are oppositely placed. One is here, the other one is in the opposite direction. So the distance increases between them, so it is trans. Alright, next is Ma3B3. For example, CONO2 whole thrice, NH3 whole thrice. They also show another type of isomerism which is called as facial or meridional isomerism. Facial is represented by FAC and meridional by MER. In facial or cis isomer, each trio of the donor atom occupy adjacent position at the corner of triangular face of octahedron, while in meridional or trans isomer they occupy positions on the corners of square planar. See here, 3 NO2 are present, so 1, 2 and 3 trigonal position. Alright, but in this case, this is FAC or cis. But if you look here, 1 NO2 is here, second is here and third is here. So they are occupying places at the square plane, 1, 2 and 3. Alright, so this is known as meridional or trans isomer. Next example is in octahedral complex. The next example is of MAA2B2 and MAA2BC type. AA represents a symmetrical bidentate ligand such as ethylene diamine, which is also called as EN, oxalate ion, which can be represented by OX, etc. So example is COCl2 EN2. Now see, CO here. CO is the central metal. Bidentate ligand. Bidentate means it can join from two sides. So En, one is here and the other one is here. And Cl, Cl are close to one another. So this is cis form. Here Cl is oppositely arranged. So trans form. And En, En. Okay. So this type of isomerism can also be seen. Now next is optical isomerism. One minute. Now you come to optical isomerism. Optical isomerism is the isomers which rotate the plane of polarized light equally but in opposite direction. They are also called as enantiomers. They do not possess plane of symmetry. Optical isomers are called dextro and levo, small d and small l, depending on the direction in which the plane of polarized light is rotated. Now, if it is towards right side, it is D, and if it is towards left side, it is L. Optical isomerism by square planar complex is not shown because it contains a plane of symmetry. So, the molecule will be exactly divided into two equal halves by the plane. Tetrahedral complexes which contain 4 different groups do not show optical activity because these complexes are very much labile. Thus, it's not possible to isolate optically active compounds. Optical isomerism is common in octahedral complexes which have coordination number 6, and it involves 1, 2 or 3 symmetrical bidentate